Good morning to dear participants. There is some network issue from from Puneet sir's side. We are resolving it. We will be starting in 2 minutes. In the meantime, rest of the participant will also join. Thank you. Yeah, good morning, Puneet sir. Is it fine now? Puneet sir, good morning. A small announcement for all the participants. There is some technical issue. We are trying to connect Mr. Puneet Goel. Just give us some time.
I didn't think it is that big. So I hope we are downloading the right stuff. Yeah, but it will complete soon. Already it has downloaded some 150 megabyte. Okay, so it's done. Okay, so we are already into that directory and we can just run that command to find out which version. So we don't, these are some previous versions. We'll be selecting version 2013, but with a later tag. Okay, so we'll select this one, the last one. Okay, the other ones are for other Intel SoC processors. So we don't look at those. So now say git, I'll say git checkout, and I'll give that version that I'd selected. So this version will get checked out. Okay, so now that this is checked out, I need to follow instructions which are make proper and then this instruction. So we have to do it for Cyclone 5. So we need to make the config and then make, and that's it. So we say make mr proper. So this is what I'm saying, mr proper. And then I'm saying uh, this command which I copied from there. And now I can say make. So this will take a bit, but not too much time, so it will finish quickly. So see, what we are doing here is we are, because we have a new RBF file, and along with that, we need to put a device tree and everything. So we are creating the U-boot process. The rest of the Linux system will take it from from Terra 6 site only. So some of the things we take from here, and then we have already made, then we have to make a boot script. So we are almost done. It's not going to take too much time now. So I copy this stuff and go back to my window here. And here we go to dot dot, and we do edit boot dot script. And I copy this stuff. I don't need to make any changes here. Yeah. And I exit window, exit Emacs window, and then I need to go to Firefox and follow the instructions. So I created a boot script, and then I need to just say this instruction. Okay, so I just need to make sure I've done it at the right place. So I had made, and then I had done dot dot. So U-boot image has been generated, and I create this boot script now. So just a minute, I need to copy this command. Yeah. So this is done, and then I have to complete the device tree. Before I complete the device tree part, there needs to be some change which has to be done manually into this file, and so I need to comment out the LED stuff again. Okay, and finally I'll do the SDC the device tree generation and compilation, and that's it. So that will complete my stuff here. So then there's still something to be done uh, for the test bench to run on the kit. So I'll quickly try to finish it. Okay. So this is where we are, and we need to, for PWD, this is where we are. We want to be there only. And I open an Emacs window, and I need to open the XML file. I hope it's XML. Yeah, it's XML. So G, and it's the HPS common bot info. This is the file we need to open, and we need to search for LED PIO. So wherever we find LED PIO, those 3 lines we need to comment out. So this is like there was the device tree will also have information about GPIOs, and some of the GPIOs are getting connected for the LED project that was earlier done. I mean that's what we didn't do it, but that was the golden hardware reference design. So we are not using those GPIOs, and therefore the device tree shouldn't have information regarding those, and that's what we are trying to manage here. So I made all the comment, all those lines commented out, and then we can come out and follow the rest of the instructions. So now I need to generate the DTS file, and this is the command. So I copy it here, and this should be quick. Okay, and then we go back and we generate the DTC file. So DTB file actually. DTS is the device tree source, and DTB, which gets generated by the device tree compiler, is the binary that gets used by the by the Linux operating system at boot time. So I copy this command and I go to my external window and paste it here. So this will complete the DTC generation. Okay, now it says dump it on a disk, on a SD card. I have actually already completed this process because even if I do it as part of the session, I can't do it from my Windows machine, so you will not be able to see it. And the VNC server I'm running, it's lying at some distance. So I'll have to go there and put the SD card in there. So to avoid that, all that hassle, I have generated all that. I have put everything there, and I have completed this process. And then uh, instead of accessing that machine using putty, we have that board connected there on Ethernet. Okay, I have a Ethernet cable into there because we'll be transferring our test case from another Linux machine over to that machine. So that's why I've connected it using Ethernet so that transferring of files can be easier. So now I'll go back here and I'll run a command called screen so that I can be on this machine and I can split the window. Okay, how to split this window now? Control C, just first time. It's not doing it anyway. So on my so I'm still on. If you take a look, I'm still on a Linux machine, which is okay, uname -a. So I'm still on Swasti, which is my server machine, and it's an x86-64 machine. So from here, what I'll do is I'll log in into my SOC FPGA. Okay. And actually I have to log in as root because that's how you log in into there. There's only root account by default. Okay, so it's already logged in. If I say uname minus A, so you will see this is SoC FPGA and this is ARM version 7 Linux. Version 7L, I don't know what L would mean, but this is actually ARM Cortex A9 and version 7 is the instruction set that ARM Cortex A9 takes. So it's the 32-bit ARM machine, okay? Okay, so I go back to my server and on my server, I put the path to the release, to the beta 9 release. And then I go to workshop, and I go to AVMM SHA3. And inside that, inside the sim directory, I have a lot of stuff now. So there is a makefile specifically for creating the E10 Nano. I'll open that file and explain the stuff to you. But before that, I need to do some cleanup here. So instead of sim, I'll create a directory EMU, which is for emulation. Okay, we are not doing simulation, we are doing emulation. All right. So then we'll copy some of the files from here. So let's not copy the DE10 executable. So let's copy the makefile. Makefile is the important one. And let's copy read dev and write dev. So I'll explain what all that is about. And we copy it to /emu. Okay, now that's done. So we go to /emu. And there we rename this file to, I'll check in all this into GitHub, so you don't need to worry about that. And over here, there needs to be a small change. Instead of this coming from bit.op, this needs to come from some other library. So when we compile, it will tell us. So let's go to EMU and just say make, and make will actually do it for if you go to EMU and open the make file, then it's going to make read dev and write dev, and it's also going to make AVMM SHA3DE10 for us. So I'll spend a little bit of time discussing all this in a few moments. But before that, let's just say make. So this is the warning we are getting. So instead of bit off, we need to pick it from volatile instead. So we'll do that. Okay, so we open read dev, and instead of bit off, so this file I had written a couple of years back. So instead of from there, I need to read from volatile. Okay, and again into this file, same thing here, volatile. And once that is finished, we can open the xterm again and say make again. So now no warnings should come. Okay, so those two files also got compiled again. Okay, so a couple of things. One is this make file that we have written specifically for creating the ARM binaries, ARM test case that we'll be running on the kit. Okay, so you can see we are using C compiler, which is ARM specific, and then having passed that to LDC2, we also need to we need to tell LDC2 that we are compiling for ARM Linux. And this is the ARM architecture we are compiling for. So it is HF, that means the floating point is implemented in hardware. Now this is also important. We are telling it that the version that we are compiling is for Cyclone 5. So what exactly does it do? So if you open the test bench, and there's a file specifically for DE10 now. I showed it to you yesterday, and there are some parts in here which say stuff like cyclone 5. So let me search for cyclone 5 and it will be clear to you. So this is the portion. Okay, and I still need to tell you why it is from FF2. I'll tell you in a few moments. But this is the portion which we want to include now. So when we say in D language, when we say version cyclone 5, and we compile it with minus D version cyclone 5, then whatever is inside, so we can have multiple version flags, but whatever is inside that version, this code will get compiled, otherwise it won't get compiled. Okay, so we are saying that, and we are providing what operating system and what machine architecture is going to be used, along with the C compiler that needs to be used. So when we do that, it generates a binary for us. So we'll say make again, but everything is done. So I'll say make clean, and I'll say make again, so that we can note the commands. So see, this is how our test bench is getting compiled. So it says LDC minus M triple ARM Linux something something, and then minus version, and then minus W minus C and all that. Okay, now so right now we have compiled without minus, you notice that. So we have compiled without minus release and minus bounce check off. Okay, so this is, and we haven't even optimized. -03 is the optimization. So this is good to go because right now we'll be running this on the kit, and since we haven't done it earlier, so it's important not to have optimizations, so that if there are some for example assertions and other things, so this is not a release, this is a development version, and that's why you don't want to give a minus release flag there, because otherwise the assertions and everything will be switched off, and if there are some runtime errors, then those won't be flagged and some segmentation fault will come instead. So we want to have those runtime errors, if any, so that though the binary will run a little bit slower, but we still will get those errors if there are any. Okay. So what we need to do now is to transfer this file to SOC FPGA. So we do rsync -avzp this file to, and before that, we can also check just to make sure. So this is the file, and we need to make sure we can run file on that just to make sure that it's properly compiled and it's for ARM only. Okay, so this is what I get. This is ELF 32-bit LSB executable ARM, and then it says dynamically linked. Where is the interpreter? And it gives some other stuff which is for not so useful for our purpose. Okay, so now we'll say rsync this file into root at SOC FPGA, and then colon. So it will get transferred there, and let's name it with a different name over there. So let's call it just SHA3. Okay, so it got copied. Okay, now we'll run it over there. So over to that machine, and we'll see there is a SHA3 here in the end. So since I had also done this process earlier, so that file is also lying there along with read, write, etc. But this is what we have copied right now. Okay, so before I run it, I go back I go back into Emacs just to know what flags to give to it. And yeah, so then I go to simulation directory because the flags are in the makefile over there. And I open the makefile, and these are the flags to be given. The same flags will run because it's the same test case that we are going to run. And then we'll try to override the factory and all that stuff also, just to run the other test cases. So verbosity, I'm not going to touch. Okay, let's get verbosity also as none. So I copied this. Then I go to this window and I copy the stuff. I just say SH3 and I will copy the whatever string I have copied from there. I copy it there. So okay, so it says Z3.so not found, and for that I have already copied it into /lib area. So we'll put that in LD library path. Okay, so LD library stuff is not the best thing to do. It actually is considered slightly evil, but for now I will do it. But later on, I'll also modify the binary so that we don't have to do it. Okay, so there has to be an export with it because we are setting it for the first time. And then when I say the old command, so it still says cannot open this object file. So probably I have some issue with this LD library path. It should be LD library path. Okay, now. So now you can see the whole thing is running. And actually, you can see we did 1,000 transactions and it finished so quickly. Okay, but what is, so instead of none, we'll change the test case so that all these messages don't get printed. It will run even more quickly then. So we come here over to the test bench, and in the test bench, I still need to explain you where this number came from. So in the test bench, I need to look for all the infos, UVM info. So this one is with debug, which is nice. This one is also with debug, which is nice. Debug again. This is the one when I'm saying matched, I'm saying it with none. So I say it with median now. Okay. So having done that, I can close. And actually, I also want to run it for 10,000 cases just to know how much time it takes. So let's do that. So instead of 100, instead of 1,000, I make it 10,000. And then I close this window. And here I am in the EMU part. I just say make. All right. So the test case is made and I copy it. Rsync again. Okay. And I go to this directory and I run it with none. Now those messages won't come because we have reduced the verbosity of the messages to medium. But now it's running for 10,000. So instead of 100 that we run on with our simulation, we are running it for 10,000. So in simulation, 100 test cases take uh, about 20 seconds, and I expect it to take a similar time with 10,000 here. Yep. So we can run it with time command just to know how much time it's taking. It's taking about half a minute. So, we have a speed up of approximately 50. So it has taken about half a minute, a little bit more. So we have a speed up of approximately 30 times. Okay, because we are running 100 times the sequences, and the so with another test bench and another DUT, which was slightly bigger, I had got a speed up of 100. So this one, because the DUT is smaller, so I'm getting a speed up of 30. Okay, now a few things. We can still have the factory. Okay, so let's do that. So I'll because I don't want to run for those many again and again, and thereby waste some time. So what I'll do is I'll add it slash test bench, and I open the test bench and make a change here. I'll change from 10,000 back to 100. Okay, and I'll close. And then I'll compile again. Yeah. So once I compile again, I'll move this file using rsync, and I go to this area and I'll run it with velocity none. So it's quick because of the only 100 sequences that get generated. Then I make UVM set override type override equal to AVMM SHA3 dot that was what sequence was that SHA3 sequence item, comma AVMM SHA3, that's the module name, SHA3 sequence item, and then for example there is one with empty packets. So this will run very quickly because the packets are all empty. And then we'll try other ones. For example, REM0. So this generates slightly bigger packets, so it's taking time. Okay. So now let's see. If we go back into the window of class component. So I don't know why these messages are coming. Is unknown. Wrapper 0. So let's ignore those. So because I'm running, so that was some other message. So because I'm running screen, so therefore what I see on the top is not actually the messages. So what I need to do is instead I can run it with more, and then I'll see those messages. We are still not proper. So yeah. So now you can see. Now you can see override. This is the override happening. And these are the classes which got registered with the factory. Yeah. So the same way, and the same, actually the same test cases would be run that way. So when I do it without more, takes about 3-4 seconds to run. And when I do it for remainder one, that also will run. So these are the factory messages that you are getting, and it takes about 5 seconds to run. So it takes much more on the simulation. It takes so less on emulation because the design is already compiled. If we do it without override, so that gives us an idea how much speed up is there uh, because it's only taking less than a second, and over there it takes about 15 seconds to complete the simulation. Okay, so now one more thing, we need to make sure that when we run it with medium, and all those messages start coming in. Okay, so I can do it with Go, for example, so that I can see these messages. Oh, again, I skipped. So the point is, when I look at the last transaction, it should be same as the last transaction of simulation. We just look at the last few words here, 158, 105, 237, right? And we go back here and we go to the simulation, and we say make clean make. Here you will notice when we compile the test bench for simulation, it takes much more time, and that's most of it is because of the linker. The linking part takes more time on a Windows machine or on a Linux machine for uh, for um, for the reason that we are using shared libraries when we link here, and when we link for ARM, then we don't use shared libraries. We use normal .a files get linked, and that happens much more quickly. Okay, so now we'll say make run. Actually, we want to run it with the same arguments. So we uh, do it here, and this is how I'm going to run it. So we just need to notice what's the last few last few numbers that get printed in the last transaction, and we need to match it against what we are getting on ARM. So I need to T it so that I can see it later. So T into sim.log. So this is called randomization stability, that or it is called portable stimulus as well. Randomization stability is where if you are running simulation in the same on the same design using the same tool, then if you run it twice, it should have the same randomization, because you want your test cases to be repeatable and yet random. So it's not actually random, it's pseudo random in that sense, because it's oh shit, I have to do this again. So it's pseudo random in that sense, because random would mean it's not repeatable, but we want to make it repeatable. So it's pseudo random. why we need to make it repeatable. For example, if a test case fails and we are debugging it, so we run it again after a fix. So we should be able to repeat the same random pattern. Otherwise, we won't know whether the bug is fixed or not, because if it's a different random sequence, that random sequence may not expose the bug. So all the test cases in system Verilog or in embedded UVM which are random, are pseudo-random, and in that sense, okay. So we are towards the close of this log file. So I'll go slowly, just so that I can notice, or I'll open it in Emacs actually, wasting time like this. Okay, so this is towards the end. Okay, so here we are getting 244, 12, and 96. I think it was different there. So there is some difference, and we need to find out why they are different. So probably it's a different seed or something. So let's make sure why they're different. So there could be different reasons for them to be different. So one of those is that I'm using uh, Z3, and the version of Z3 for the two needs to be matched. And one is maybe I'm not sure, but maybe Z3 gives different results on 32-bit and different results on 64-bit. That we need to find out. So what I'll do is I'll open Emacs and I'll make a comparison between the two test benches. And let's see. So this one is running with seed. The seed given here is 1. And this one has a seed which is again 1. So I'll have to debug why the test cases are slightly different. So, but let's not go in too much into that right now. So this part is not finished yet. I have to explain you a couple of things. One thing is the two files, which again I'll upload on GitHub. So one of the files is read dev and the other is write dev. Okay. So what are these two files for? So these are for debugging. These are for debugging. And why I created these, in case my test case won't run on the Cyclone 5 board, D10 on D10 Nano, that's the name of the board. Then I want to debug whether my design is properly gone into the FPGA. Right now, they are running perfectly because I'm getting a matched everywhere. So that's why I'm confident it's running perfectly, because the stimulus is going inside FPGA, the FPGA is processing it, and the end result is coming back. But then if I want to basically, if something was not running and I want to debug it, so how to debug it? That's what this is about. So read dev basically creates this device, and this device is basically nothing. That you have opened virtual memory, and as you can see, we are also destroying this virtual memory map in the destructor, and there are read and write functions for reading or writing into memory location. So this read one just calls the read function. It creates the device and calls the read function. So we read from a particular address and display it. And similarly, there is a write one which is for writing into a particular address and displaying it. So how to use these two for debugging? So let me tell you. Okay. So first, what's the usage? Usage is we have to give this command along with the address. And then I also want to know whether the address will be byte address or word address. So I give address as ADDR and it gets divided by 4 over here. So it's the byte address. It's not word address. Okay. So now if we remember the different blocks that we had in our design and starting from 0x200, starting from 0x200, I was having a read write block, and in the end at 0x300 I had a read only block where the output of the module would come. Okay, so this I'm explaining, like if you are doing a project yourself where you have put something into the SOC FPGA and that has a register map. Obviously, it will have a register map because the only interface that becomes available to you is through the Avalon bus or some other bus where it's a memory map bus. So if you want to specifically test something by reading or writing into certain locations, so you can do that. All right. So here what I'm doing is I take the arg, whatever arg is given to me, I take it, convert it into integer, and then I read from that location. So let's try it. So I want to first write into say 0x200, and since it's an hexadecimal 0x200, so that will become 512. Okay, because 100 is 256, 16 square. So 200 is 512. So what I'll do is I'll say, okay, I have to be on the page. So I'll say dot slash write and write device, and first, so it will give me what's the usage like. Let's see. So the usage is write device. So the usage is write, and then I have to give address and data. So let me give an address, and the address is 512, and the data I want to write there is 42. Okay, so 42 got converted to decimal, it becomes 2A, and I have written it into the device. I didn't get any error. So now I'll read from the device because this part of the memory is read write. So probably it should read the same. I don't know how it is implemented, but it should give me 42 back. Yeah. So I read and it gave me 2A back. Okay. I believe if I want to give hexadecimal value here, that should also be accepted. So if I say 0x200, no, it doesn't like that X over there. So I can improve that so that it starts taking 0x as well. But for now, you have to give in decimal. So you can write a different value here. So say 1079, 17297, the Ramanujan's number. So I wrote it and then I read from the same address. So it reads back the same value. So I'll write it into a different location, for example. So let me write it at 5600 address. It should be in the same block because we have 200 bytes block. Okay, and then I read from 600. So I get the same value. So if I read from 596, for example, I get a different value because it's set to 0 for some reason. If I read from 516, it's some value which which the pattern we were running would have stored there. Okay, and similarly, if we read back from 512 plus 256, that will be 512 plus 256, 768. So if I put 768 over here, then I get the output that would have come into my test case, the last sequence that I ran. Okay, so these two small utilities can be used for debugging if you are working on the kit and you want to quickly find out whether your design has been properly mapped or not. So let's say now we want to read from zero address. So this is the address where the name of the whatever hardware you have created. So you have a name to the hardware, which probably is Avalon SHA3 or something. So that is stored at 0. And then at 4, so these are empty spaces because the name is small. And then we had a register map where we also had the version stored. So if we read from 8, so the version is string is getting returned. Okay. Now, one more thing which I need to explain to you, why we are taking this 0x, this particular value over here. So it is 0x ff2 00000. So there are 5 zeros in the end, and the value is 0x ff2. So I don't remember the website, that's why I try to remember this value. Okay, so when you go and search for BE10 nano and you search for 0x ff2 00000. So this yeah, this thing comes up which tells you the first offset address is at this location. Or you also have Intel website. Okay, probably maybe somewhat better is to search for Cyclone 5 instead of this. Cyclone 5. And you have Intel website come up, and there you will see this address out somewhere out here. This one. So it says FPGA slaves accessed via lightweight HPS to FPGA AXI bridge. Okay, so this is the start address. This is how Intel has mapped it. Okay, so this is the address we are using as an offset address, and our module, if you then bring up whatever, so which one is it? So we worked here in this area, and we had this one, and we had the device tree generated. So the device tree will be inside this. This one, device tree source. So our module, that is SHA3, if you locate here, then it is having the address map here, register addresses. So see, the other modules which are not starting from 0, which are starting from some offset. Our module is starting with 0. This is the offset. This is the step, and this is the offset. Like basically, it means to say that you can have a step of 1, and this is the offset. These are the total. So as I in the RTL, we found that we have some memory block in the beginning where we have the control and status registers. Then starting from 200, we give the input. Starting from 300, 0x300, we get the output. That's why it's ending at 400. Okay. So this is our address space, and since it starts from 0000, and we have to add the offset of the whole FPGA itself, because all the slaves that will reside on the FPGA will have that offset in the address decoding logic. So we add this value to the offset and we get that number. And that's where we are reading or writing into. So this completes my small emulation board agenda. And now very quickly, if you have some questions on this, we'll address those. And otherwise, I'll move on to the factory method, and I'll tell you a little bit more about factory method so that your doubts can be cleared. That was the pending question. And in the post-noon session, we will cover QEMU, and we'll also cover, before that, we'll cover, because QEMU, I can always upload the stuff on GitHub and have the instructions there. So you can understand from there as well. But the virtual methods and polymorphism and how all that happens, that I need to explain to you so that you can you can basically take care of your confusions regarding stuff like upcasting, downcasting, and casting in general, what is happening there, or when a virtual function is called, what happens. So I'll take that first. It will take about an hour. And after that, I'll explain the QEMU part to you. And if some time is left after that, we'll also run it. But running will probably take some time because QEMU has to be installed and all those instructions need to be followed. But I'll explain the test bench to you, and maybe I'll run it without QEMU by emulating the QEMU, whatever QEMU will be doing on my machine itself. That will be quick. So I'll at least do that much. All right. So before I go there, I'll want to have any questions that are there. And then before we break for lunch, I'll cover the factory again so that your confusions can be taken care of. So any questions, please let me know. I'm stopping screen share and so that I can look at the questions. And right now there are 0 questions. So if anybody is having a question, let me know right now. Otherwise, I'll move on to the factory. So the factory part is very simple. Basically, somebody asked, what is the difference between calling new and using the factory to create an object? What difference does it make? And how the test case we will be able to use factory override in case we are using the factory. And by the way, when we are using type ID and something, then create function, and how factory is getting invoked. So I'll cover that first, and then I'll come to the other question. I'll come to how factory override works. So it will take me about 15 minutes to handle all this. So let's quickly get to that. Okay, so first thing, factory is like a pattern which is for generation of objects. And why it is there? Because 2 reasons. First reason is we want to have dependency inversion principle. We want to implement that for object generation as well. So let me give an example. Say I buy a verification IP, and this verification IP is coming from say TrueChip, which is a verification IP vendor. So they have a verification IP for gigabit Ethernet, and I buy it from them. So now it will be a system Verilog verification IP, and it will be coded in system Verilog, and before they pass it on to me, they'll probably make sure that I'm not able to get the code because that's their IP. They just have given it to me for usage. And in System Verilog, there is a way of handling that. So they'll encrypt the System Verilog and send it to me. So now when System Verilog part is encrypted, then there is no way I can change it. Okay, so there's no way I can even look at it, but in their APIs or in their user manual, they'll tell me what are the classes that they have implemented, and if I want to, so what are the different fields in the classes, for example, so they'll have some document which would explain to me that if I want to extend that class, the sequence item class, then how should I do it? And if I want to put some extra constraints in the extended class, then what are the different elements I could be constraining? Okay, so either this or some part of the Verilog code or system Verilog code, they won't encrypt, and some part they'll encrypt, the other part they'll retain its visibility by not encrypting it. So this part either is visible to me or it's written in the document how an extension needs to be done. Okay, so then what will happen is, so then it will be something like this. So their sequence item class, which the example I was discussing, that was for Ethernet. So it will be something like this. This is a sequence item, and there are going to be elements over here. So this portion, maybe it's visible to me. Constraints may not be visible to me, and some other implementation functions that they would have written won't be visible to me. Or if this is not made visible to me, then probably they will put this part in a document so that I know how to extend it. Okay, so then I'll extend the class. So this I can do in my workspace, so I don't need to touch their code. So I'll extend their class, though this class may be encrypted, but doesn't stop me from extending it. So encryption, the way it works in Verilog world is, it no longer is human readable, but it's readable by the machine. So machine knows, or a compiler knows how to decrypt it, but a human doesn't know how to decrypt it. So the code will not be visible to me, but the essence of the code or the intent of the code will not change. It's just that it's written differently. Okay, so the class name will not change. It's just encrypted. So I'll be able to extend it. I'll be able to put extra constraints on it, or if something else is required, maybe instead of normal Ethernet packet, the extended packet is having encryption of payload, something like that. So that extra part I'll be able to code as in the extended class, and that's the open close principle. Now I want to make sure that whenever a test case is creating a sequence item, then instead of that sequence item, the derived sequence item or the extended sequence item is the one which gets picked up. Okay, and it could be because with verification IPs, the vendors also provide test cases. So it could be that this particular vendor also provides me a test case, and those test cases are also encrypted. So in that case, I'll still be able to change the behavior of the test case by overriding the class. Okay, so instead of generating a normal Ethernet packet, say my derived class or the extended class is having an encrypted packet. So when that gets instantiated, when in a test case the normal Ethernet packet is getting created or instantiated, I'll change the behavior and I will be creating the extended packet. Okay, so now the confusion probably was also in that's what somebody was one of the attendees of the workshop. He asked me on a WhatsApp group. So the confusion also was, how come type ID? How come request or type ID create? So what's the use of type ID create? Okay, so now when we do object utils, so here I'm doing object utils, for example. So, but this is a request class, so basically I'm talking about this class. Okay, so when I do object utils, this will, because it's a mixin in system Verilog, it's a macro. So some code will get inserted here, and that code will give me a method called type ID. And that type ID will actually, it doesn't give me a method called type ID, it gives me a class named type ID. Okay, so when that also has a create function. So that class is the interface class for the factory, and the create function will actually invoke the factory to create an object. So by default, the factory will create an object of SHA3 sequence item type only. But if I place an override in the factory, then it will create an object of the derived type that overrides SHA3 sequence item. Okay, so the example is here. So we come
Hello,
here
sir.
and we say,
Actually, your screen is not shared, sir, right now.
all right, sorry about that. It's such a confusion. So I'll have to repeat a little bit after sharing my screen. Share. All right. So hope it's visible now, and I'll do that portion again.
Yes, sir.
So
Your
what
screen
happens
is
is,
visible.
so I was saying this mixin brings in, because some code is getting, by way of mixin, actually in embedded UVM, it's mixin, in system Verilog, it's a macro. So macro, brings in some code. So that code has a class named type ID. So let me show. So we go to code and we go to EUVM. We go to source, base, source, UVM, object defines. Source will have UVM and base. And then there'll be UVM object defines. There's some similar code in system Verilog also. And there you can search for type ID. So see, type ID is an alias to a class, object registry class. And this class knows what type it's getting instantiated from. So in case you have a background in system Verilog, you will have to do something like this over here. So in system Verilog, it will be tick UVM object utils, and then we will be providing SHA3 this way. Here it automatically infers the class type, but there you have to provide in system Verilog, you have to provide. Okay, which is slightly error prone. If you by mistake make a typo here and put some other, or say you have copied the class and then you change the name of the class, but forget to reflect that change in the UVM object utils, then there'll be bugs, okay, which will be difficult to catch. But here it automatically infers in embedded UVM. So it invokes the object registry. And this object registry mechanism, you can see it's taking something from the factory. And so that's slightly more complicated than what I can tell you right away. But type ID invokes the interface to the factory, and therefore, when I say create, so this object registry class. Okay, let me go a step deeper. So you can open registry, UVM registry .d, and here you will see a create function. Create, okay, which is implemented in the common type. Yeah, create. Okay, so when you are invoking create, then since it's a parameterized class, and the parameterized class knows what particular uh, what particular object it is meant for, so it will be actually using create by type, and this create by type is also implemented here. So then it invokes the factory and create the object by type. Okay, so this is the little magic which is happening inside. So it's actually invoking the factory when you are saying type id dot create, or in system verilog it will be type id colon colon create. So it invokes the factory, and since it's invoking the factory, in case there is a factory override, type override in factory, then the actual object which gets created will be slightly different. It will be of the extended type, not of the base type that we are creating. Okay, which I already covered earlier, how that happens through associative array, and how for every type that we register with the factory, the name of the type basically has an object stored in the associative array. Yes, sorry, there was some disruption. So it basically is in the factory that we store, corresponding to every type name, we store an object, and when we have the factory override, then object of the, just give me a second. I have some personal thing. It will take me a minute, so I'll be back. Just give me a second. Okay, so I'm back. Sorry about that. So when there is a factory override, then the derived, so then the base class name will actually have a derived class object stored against it. Okay, so and that's how then the cloning process. So it's slightly different than that. So it's not the derived class object which gets stored there. It's a representative. So it's a wrapper class which gets stored there, which knows how to create the derived class object. Okay, so this is how it is happening. When we are invoking type ID, it is invoking the registry, and the registry is the interface with the factory. And when we call create, then it's the factory which is creating the object. And when we call new, then the factory doesn't come into picture, and we are calling the constructor directly, and thereby the new object will be created. If we call create only, then the factory override will happen. Otherwise, with new, factory override will not be executed, because we are just saying new, and we are very specific that we want to call the constructor of the class, nothing else. Okay, so if still there is some doubt, we can take it up offline on WhatsApp group, or I mean, that's all I wanted to explain. And if you still have doubts, so please ask on WhatsApp and I'll respond. So we'll have a break now, and we'll get back at 12:50. And when we come back, I'll be taking up a few slides for explaining to virtual functions and downcasting, upcasting, what all those concepts are. And then after that, we will handle the QEMU portion. So we'll meet back at 12:50 and we'll break for lunch now. So do have your lunch, because after 12:50, when we meet back, we'll have a session for 2 hours, a little bit more, up to actually, yeah, for 2 hours. That will be exactly 2 hours, and then you will have a test also. So this is the time for lunch. Okay, and when we come back, you can ask questions. So I'll spend a good 5 to 10 minutes on questions if you have any.
Hello, Puneet sir. Hello, Puneet sir.
Yeah, sorry, I had skipped. So we have a break for half an hour. We'll be back at 12:50.
Okay, so just one announcement I need to make. Yeah, all the participants, I request you to please note that due to the delay in today's class, we shifted the class till 2:45. The quiz will be from 3 to 3:30. We have already updated the information in our Google Drive. So I repeat, the quiz timing will be from 3 to 3:30 p.m. today. Okay, thank you, sir.
Okay.
Hello, good afternoon, sir.
Yeah, good afternoon. I said we can meet at 12:50. So just give me 3-4 minutes. I have to transfer slides to my Windows machine.
Okay, sure. Yeah, thank you, sir.
Okay, so there are a few questions. I'll take up the questions first. Sir, some of the commands that we are unable to get, so can you share something about it? Okay, yeah, I will be updating the website. I'll be putting the stuff there. Just that, making all these slides and multiple choice questions and everything kept me so busy with the training that I was unable to do everything that I promised. So, but don't worry, I'll do it. So, um, I'll update the website, put all the commands there in the forum, and that's how we'll go forward. So this is like, don't take the workshop as end of it, end of our interaction. Uh, I'll update the website, and if in future you have some query, you can put it on the website, and I'll be sure to answer it. Okay. Then YouTube streaming was not getting required bandwidth. Finally solved the issue. So that was the only query. And now I have still two things left. One is I have to go through the slides. Okay, so I'll share my screen. Give me a second. Let me open the slides. All right. So how to share the screen here, and there you go. Okay. So I have very few slides today because the topic is very specific, and I have to discuss how polymorphism, what polymorphism is. Actually, we talked about a lot of object-oriented principles. Now, polymorphism is the basics of all those principles, like starting with open-close principle and list of substitution principle, as well as dependency inversion and the interface segregation. All of them assume that you will have some sort of inheritance and virtual functions. Now, in this session, we are going to have, we are going to go a step deep, and we are going to look at what polymorphism is. And actually, we are going to also look at what happens when you inherit. So how the virtual functions kick in and how they get invoked. So a little bit of fundamentals, and that I believe is good for clearing most of the doubts. So let's go ahead. Okay, before we go ahead, since even if you work on system Verilog and you are not using embedded UVM, there will be reference models, and if you are interfacing with emulation platforms or virtual platforms, because if you are doing verification, then that kind of interface is also your job. So if you are doing all that, then you are supposed to know a little bit of C++, and this part I don't see covered at many places. So that's why I have a slide on this. Even if you read good books on C++, most of them don't deal with this part. So this part is about C and C++ declarations. And just give me a second. I have something to close there. Yeah. So this is something which you don't see at many places. Like, for example, a lot of people, when they come across some declaration like this one, like the one on line 7, they simply don't get what it means. Okay, it's only with a lot of experience that you start getting to know how to read this. So let's see how to read a declaration. So the first part of reading a declaration is finding out what is getting declared. So with every programming language, there'll be keywords, whether it is D, C, or C++, or even system Verilog, they are going to be keywords. Okay, so the point is, first you filter out keywords, and what remains, then you figure out what is getting declared there. For example, let's start with the first one, int const pointer volatile IVC. So if you filter out the keywords, volatile, everything in green over here is a keyword. Everything in blue over here is a built-in type. Okay, so anything else is what is getting declared. For example, is the IVC variable over here which is getting declared. It's the data as an array which is getting declared. It's again data, and it happens to be a function pointer, so which is getting declared. So no, it's not a function pointer. It's a pointer to an array with 5 elements. So I'll explain how to read that. This one is a function pointer, which the one on line 7 is a function pointer. So this one, we'll see how to read it, and we'll see how to read each one of them. So the first one, we first take out volatile and constant, in the sense that we want to find out what is getting declared. So it's IVC which is getting declared. Now this is how to read it. First go to what is getting declared. So IVC is getting declared. Now this one is simple because you are here. So there's only one way to go, that is from right to left, because on the right side there is nothing. So you go here and say IVC is a volatile pointer to a constant integer. Okay, so it becomes very clear that constant is getting applied to the integer, not to the pointer. So it's the value which is constant, not the pointer, not the address. And what is volatile? So IVC is a volatile pointer. So the pointer is volatile, not the value in there. So it's usually the address which is volatile anyway. All right. Now, volatile, I already explained to you during the session, like what volatile means when you want to avoid cache, and that's when you start using volatiles. Okay, so I already explained when we work with the kit how the hardware will have to be declared volatile, because when you are accessing the hardware, then you want to bypass the cache and directly access the hardware so that you get the right data. Now, the same way, we'll go over the second one, data. Okay, now data is having something to the right. So we read it like this. Data is an array of 5 elements. And then because we already are talking about elements, so those elements are of type constant pointer double. So they are constant pointer of two what? Two double. So now the pointer is constant. Okay, now let's read the third one, data. So we start moving to the right. So the first thing, once you get to where you want to, I mean, first thing is to find out what is getting declared, and here it is data. So now when you reach there, the first thing is you look towards right, like we did here. In the first one, there was nothing on the right, so we have to move left. In the second one, there was something on the right, so you read that first. Now the third one, when you start looking towards right, there is a bracket. So we have to stop there. Okay, so that's how you will read it. Data is a constant pointer. Pointer is constant, not the value inside the pointer. So data is a constant pointer. Then you again hit a bracket. So now you come outside the bracket and look towards right. So data is a constant pointer to an array with 5 elements. And now that we are talking about the elements, what's the type of the elements? The type of the elements is double. So data is a constant pointer to an array. So every array will also have an address, right? So data is a constant pointer to an array, and that array is of 5 elements, and each of those 5 elements is a double. So still, many of you will find it too complicated, like what kind of data structure we are trying to, or what kind of pointer, what actually does it mean. So that will come with experience, but at least you should know how to read it, what actually is getting described. So data is a constant pointer. So you are trying to say that the array which is there, which has 5 elements, the address of that is stored in data. Now data, since it's a constant pointer, and since data is, so this pointer, you are not supposed to modify. You can't have another value to it. Okay, the first one, it wasn't the pointer which was constant, it was the value inside the pointer, what is stored inside the pointer, that was constant. Here the pointer is constant. That means the address of the array as stored in data is a constant. You are not supposed to modify it. All right, so data is constant. Data is holding a pointer, and that pointer is constant. The third one, again, data, because everything else is a keyword. So it's the data which is getting defined. Data is, now you go towards right, there's nothing. So you have to look towards left. So data is a pointer. Now that you have taken care of the brackets, you look towards the right. Now you have an opening bracket. And what is an opening bracket for? Opening bracket means function. So data is a pointer to a function which takes 3 arguments. Now, what those arguments are, we will come to that later. So data is a pointer to a function which has 3 arguments and returns a reference to a double. Okay, so first you look towards right, there is nothing. So you look towards left, there is a pointer. So data is a pointer. Then since you hit the brackets, so you come out of the brackets, data is a pointer too, and then you look towards right and you find it's a function declaration, which takes 3 arguments. And now that you know this is a function, so you know that there are arguments and there will be return value. So this is a function and the return value is reference to a double. So what is data in the first place? It's a pointer to a function. And what is that function? That function takes an integer, a double, and then again it takes because this is again a function pointer. So it's a pointer to a function which takes int and doesn't return anything. It's void. So our function that we are declaring, a function pointer actually takes 3 arguments. One is data, one is integer, the other is double, and the third is again a function pointer, and it returns a reference to a double. Such a function, when it is there, data will have its pointer to such a function. So pointer to such a function will be held in data. So last one is a type def. You have type defs in system Verilog also, but they won't get so complicated because there are no pointers. And in system Verilog, for example, you can't have a function which takes a function pointer because there are pointers, right? So there's no, you can't have a function as an argument to another function because that will happen only through pointers. But let's read this one. So now it's a type def. So instead of defining a variable, you're defining a type. And again, you filter out all the keywords. So you remain with function pointer. So a function pointer is a type which is of type pointer to a function which takes an integer and returns a double. So function pointer. Now the name is suggestive, and that's good that the person who wrote it had a name, had a variable or type name which is suggestive. But what exactly it is, what kind of function pointer it is? It's a pointer to a function which takes an integer as an argument and returns a double. So func pointer is a type. And now here, since you're using func pointer, so data becomes of type func pointer, and then you'll read data is an array because you look to the right first. So data is an array of 10 elements, and each of those 10 elements is a function pointer. All right, so this takes a lot of pain out of reading C or C++ code if you master reading how to read a declaration. So I have written it in text how to determine it, but it's more or less what I said. So I'll still read it once. First determine what is being declared, and I told you how to basically take out all the keywords. So you get to, so if something is not a keyword or a data type, or a user-defined data type, for example, user could have defined a class, so that is also becomes a user-defined data type. So when you take out all of that, then you get to know, okay, this is what is getting declared. Look to the right until you find an unmatched closing parenthesis. That is the round parenthesis, not any other kind of bracket. Read everything between the name and that parenthesis. So when you do that, when you're reading towards right, then you read towards right sequentially. Okay, and then when you finish that, then you read towards left sequentially, one at a time. Move to the left to the name of the name until you find an opening parenthesis, and interpret everything between the name and that parenthesis, reading from right to left. Okay, first you were reading from left to right, now from right to left. Now repeat that process by first looking to the right of the closing parenthesis found earlier, and then to the left of the opening parenthesis just found. So there could be multiple parentheses, for example, kind of recursive parentheses inside parentheses when the declarations become too complicated. So that could also happen. So, but this is the process to read it. Okay, now we come to, so this is slightly a topic which we missed earlier, and this is about what virtual memory is and how when we are doing that lab where we are running the code on a board, then when you're doing virtual memory mapping, and what actually is happening. So whenever you have code and it gets compiled, the compiled file will look like this. It will have a header section which will describe. So this all will be binary, by the way, right? So this is the ELF format, and this is how a file is stored on the disk before you execute it. So the header section, again, it will be in binary. You won't be able to read it without interpreting the binary values. So the header section will have information about the rest of the segments, like what all is there inside this executable. So this is the meta section, in that sense that it has information about the file itself. And then you have machine code section where your executable code lies. This is the code which actually will get executed. Then you have initialized data section. So any global variable or any static variable. So what's the difference in C or C++, or for that matter in system Verilog or D between a global variable and a static variable is both are of global scope. That means they will be there right from the beginning to the end. Okay, so they are global in that sense. But visibility will be there. There'll be visibility of the, so if you have a static variable inside a function, for example, so it will be a global variable in that sense that it will go into initialized data section and it will be there from the beginning to the end. Okay, so in the scope, it will be global, but in terms of visibility, it will be local. Okay, so all the static and global variables, whatever their values should be, since you are going to execute the code, all those will be loaded. Those values will be loaded in the beginning. So all the init values for all global variables and static variables will be stored in a particular section. So when you are writing code, so if you have a global variable or a static variable, you have the option of putting an initial value into it. If you don't use that option, if you don't initialize the variable, all the global variables and static variables will be automatically initialized. Okay, so for example, if you declare an int, it will be initialized to 0. So that way, so those values, because those are init values, those have to be loaded in the beginning. So this is where inside an executable it will be stored. Then you have a symbol table section, which is mostly for linking purpose as well as for the purpose of debugging. So you could strip this section in case you are making a release, for example. If this is an executable, for example, you can strip this section and make a release. But these are these symbol table section will have the names of the variables as you declared in C, C++, or the labels that you declare in assembly. So these are those variables or symbols, and these are useful for debugging. But otherwise, this is just a if you are not debugging, this is a waste of space. And they are useful for linking in case you are having, this may not just be an executable, it could be a shared library. So then it could be useful for linking, for example. Now the code part of your file will be loaded in certain memory space, and the initialization part will also be loaded in certain memory space. Okay, when you load, basically when this loading means when this we are executing it, so this module gets loaded in memory. Okay, before the execution can start. So that's the functionality of something called a loader. Like when compiling, the final step is a linker, and when executing, the first step is a loader. It will load it into memory. Now this is where virtual memory comes into picture. Okay, now the processor. So you had old processors like the 8085 and even 8086. Now those processors only allowed one task at a time. But 80386 onwards, you have possibility of something called multitasking. And it's because of multitasking, because there could be multiple applications which are running on the same machine simultaneously, or at least that's the difference between multitasking and multi-core is multiprocessing is multitasking could happen on one single core also. In that case, the operating system divides the time of the processor between the different applications that are running. Okay, and in case of multi-core, you have multiple processors available, and the operating system then has possibility to send one of the tasks to any of the cores that are available, any of the processor cores that are available. But multitasking can be with one processor as well. And even with multiple processors, memory is shared. All the, say, if you have 8 processors or 8 threads possible, then all the 8 threads are looking at the same memory. The physical memory will be shared. Okay, now since you have multiple tasks running, and these tasks are as if they were independent, as if they each of them had its own processor. That's what multitasking is about. So since these tasks are supposed to be independent of each other, so they'll divide the physical memory between them. The operating system will give them exclusive memory, that this part of memory is for you. And now that exclusive part of memory is given to that particular task or that particular application. That particular application, when the operating system gives it certain, for example, for dynamic data, two paths have been given to this application. Now when this physical memory is given to the application, then it's through a table, it's through a lookup table, and that lookup table will hide the actual address of the memory from the application and will give it a modified, translated address. Okay, and that's what virtual memory is. Physical memory address will be different, and it will get mapped via a table and given to the application, and the application will see the virtual address. So this is necessary for multitasking to become possible. And so basically, when you are running a bare metal program, for example, without the operating system, then in that case, it's the operating system which is making multitasking enabled. So operating system brings the processor into a mode where that kind of translation from virtual memory address to physical memory address to virtual memory address and vice versa can become possible. And so if you are running bare metal, then the operating mode of the processor is not that level, is not the multitasking level, and therefore the physical memory will be accessed directly. But if you are running an operating system like Linux or Windows or Android for that matter, so then the processor is running in multitasking mode, and then all this translation will happen to make multitasking possible. And for that reason, you will have a concept called virtual memory, which will be different from the physical memory addresses. All right. So this is what physical memory is. This is what physical memory and virtual memory concept is about. This is also important to know that static data is initialized right in the beginning. Dynamic data will be allocated by the operating system to the application, and then the application will map it to different variables, whatever you are doing here. And then the stack also is important. So basically all the local variables go on the stack, and stack is, instead of allocating stack, it's more like mapping. So if it's dynamic memory, it's through allocation. If it's static data, it will be there in the right in the beginning, and since it's static, the size is not going to change. So there is no, so the only allocation to an initialization that is there will be happening right in the beginning. Okay. Dynamic data, the application decides when it needs more memory, it will call malloc or new or whatever, and then more and more memory will become available to it. Stack will be as you call functions, and those functions need local variables, or whatever data is getting passed to a function. So that too, in certain cases, it's not necessary. It will get it could get passed via processor registers also, for example. But if that data is too big, then probably it will get passed via stack. So all that will be via stack, and stack will not be allocated. It will be mapped. It will just grow. And therefore, stack is not a costly. So when you call a function and more stack is available to you, it's not a costly operation, because it just, the pointer just moves. Okay, stack pointer just moves. And but the dynamic data allocation is a costly operation, because every time you allocate, you have to interact with something called a memory manager of the application. And if the application doesn't have memory left to it, sufficient memory left to it, it will ask the operating system, and then only the memory will become available to you. So it can become a costly operation. Okay, so having said that, let's look at, so this is the cost of dynamic memory location. I already talked about it. So let's look at now, we move into the direction of virtual functions, polymorphism, what downcasting and upcasting is about. So given a class, you could have virtual functions like this function over here is virtual. It's the print function. So let's read it. Print is a function. We move to the right, which takes OStream and OStream reference to OStream. So a reference to OStream as a pointer, as an argument, and it returns constant. So now, though it's towards the right, you are actually, this constant attribute will not attach to the return type. So the constant attribute will attach to the function itself. So let's see how. So print takes an argument which is of type reference to OStream and returns a reference to OStream, and it's a virtual function. And the function, this constant attribute will attach to the function. So that means you are telling the compiler that this function is not going to make any modifications to the elements of the class. So it's a constant function. Okay, now this is a virtual function. So you are going to have virtual functions in system Verilog or in embedded UVM as well. So in embedded UVM, actually, the way it happens in D language is that you don't have to declare a function virtual. By default, all the class functions will be virtual unless you call them final. Okay, so in case you want to have a method which doesn't inherit, which cannot be overridden, then you have to put the word final over there. Otherwise, every function in D is virtual by default. Okay, now this is one kind of functions, virtual functions. There's another kind of functions like the one over here, which is a class function. Okay, which is a class method. So X doesn't take anything as the input, returns a float, and it doesn't modify anything. So it's a constant function, but it's not virtual. Okay, so this is the other kind of function. And then there is another kind of function which is static. Point count doesn't take an argument, returns an integer, but it's static. So these are the three kinds of functions. And there are two types of variables. So you have a normal variable, which is a class variable. You can say object, every object will have it. So an object variable. And then you have static variable, which is more of a class variable. So it gets associated with the class. This one gets associated with the object. So let's see how all this works. And of course, you have constructor and destructor. Destructor can be virtual, but constructor cannot be virtual. Okay, so in C++ or System Verilog or a D language, there are two flavors of data. So one is non-static and the other is static. One is normal data, the other is static data. There are three variables, there are three flavors of member functions. So there could be global functions, but I'm talking about only class member functions yet. So there are three types. You have static, non-static, and virtual. Okay, so what happens, and this is very interesting. So for every class, this is the class. Okay, the normal data inside the class, this is float x is normal data. So it is non-static data. So it will go inside the class. So the other data was static. This was normal. So when you create an object of the class, normal data will be there inside the object. Okay, but static data will be placed elsewhere. So our static data in this case was point count, this point count. This will be a global variable in its scope. Okay, this is non-static data, so it becomes part of the object. So even if you create 100 objects of the class, this is going to be a single copy because it's static. So it's not part of the object. Okay, and in addition to the normal data, the class may have pointer to something called a virtual table. Okay, so let's take a deep breath. This is something you must understand this in case you want to be good at polymorphism and you want to know how the virtual functions work. So the class, not the object. The class will have a virtual table. Okay, so the class object will have the pointer to the virtual table, but the class will have a virtual table. So if you create 100 objects of the class, there'll still be one virtual table, but every object will have a pointer to it. Okay, so there is a float inside the object, and there is also a virtual a pointer to the virtual table inside the object. All right. Now, now all the virtual functions will be populated inside this table. So first see, so let's talk about non-virtual functions first. So there's a function, for example, out here, float x. So x is a function, and x is just like a global function, but it knows, the compiler knows that this function is associated with the class. But otherwise, it's like a normal function. The constructor, since it's non-virtual, it's also like a normal function. So even if you create 100 objects of this class, they are just like lying somewhere. So this function is in the code. This function is implemented in the code. So it's in the code memory. So it will have a pointer also. But if there's only one copy of these functions. So when you create an object, a new object, without even creating an object, these functions will be there in the code. When you create an object, then these functions will operate on that object, but they just have one copy. Okay, and then the virtual functions. We have two virtual functions. We have the destructor and the print function. Both of them are virtual. They will be populated inside the virtual table, and we'll soon see why, they are their pointers are kept in the virtual table. So there again, there'll be only one copy of these functions, but pointer of these functions will be stored inside the virtual table. So if you call function x, which is not a virtual function, the compiler is going to directly, any call to x will be translated to the pointer of this function. So it won't be directly done, it will be done at the time of linking. The compiler will only say, okay, this is the name of the function and this is what I'm called. So it will have a symbol there, and that symbol will mean that okay, I'm calling this function, and linker will say, okay, this is the place this function is defined, so this is the pointer which actually the call is going to. Okay, but for virtual functions, it's not the compiler which is deciding where this call has to go. Like when you're calling a function, then what exact memory location the execution will transfer to. It's decided at runtime through these function pointers. Okay, and in addition to keeping a lookup or some reference to all the virtual functions, the virtual table will also keep information on RTTI, runtime type information. Okay, so we'll see what this RTTI is about. So, but this is what it is about. The rest of the thing should be clear to you. Even the static functions are just like normal functions, just that there's slight difference between these two, in the sense that static functions cannot access members of the object. They can access only the static members of the object. Like this static function will be able to access the static member point count, but it doesn't have any reference to the object itself. These functions, they have reference to the object. If you're calling them on an object, they get a reference to the object. And these functions which are static, there's only one over here. Then because it is static, it doesn't get reference to the object. It's class specific, not object specific. So the virtual methods of a class cannot be static because they are tied with the, so in the layout they are tied with the object, not with the class. This is tied with the class. This is also tied with the class. These are also, because these are normal functions, then they are tied with the object of the class, not the class. They kind of get a reference to the object. So they have a reference to the object, and these ones don't have a reference to object. Okay, and these virtual functions, they are populated inside the table, the virtual table for this class. So this table is specific to the class, but the pointer to the table is carried by the object, and then there is a pointer to the functions inside the table. And the RTTI is the information of the class. So if it's point, which is the name of the class, then you can think it will be slightly more complicated, but you can think point is stored over here as a string. So that, the class knows, the object of the class also knows that it's of type point. Okay, now see the background, a little bit of background. There are programming languages which are called typed programming languages. There are programming languages which are untyped. Okay, so for example, Tickle is untyped. In Tickle, everything is a string. So even if you are adding two numbers, so each of the numbers are represented as string, and then the function which will implement adding that will convert the string into numbers, and then it will add, and the output which the user will see in tickle will again be a string. So 2 plus 2, 2 and 2 both will be strings, and addition will return 4, which will again be a string. So it's completely untyped class. There's only one type, which is string. And string will be represented, string itself will be interpreted as numbers when required, even as floating numbers when required. Okay, then there are languages which are dynamically typed, like Python, or like there is a language called Lisp. These are dynamically typed. So the dynamically typed classes will have dynamically typed, not classes, dynamically typed languages will you can have variables there, and the variables will hold a value, and in addition to value, it will also hold information about what type that variable is of. So the same variable at one point, so same variable could be holding a string. At another point, the same variable could be holding an integer, because the type information is in the data, it's not in the variable. Okay, and then there are languages which are statically typed. So C, C++, System Verilog, D, all these are, and there are a lot more. All these are statically typed. So therein, the variable will have a type, and the data which is stored will not have a type. So data will be plain data. Now, when it comes to virtual functions, when it comes to inheritance in C++, Java, or whatever language it is, then that is the point where the language slightly changes, and language has dynamic typing available. Okay, so data for you in that case, in case of inheritance and virtual functions, data is also holding type information. So this variable, this class, which is of point type, but it's limited dynamic information. So, you can't, for example, convert a point, which is like this class object point, to any other class, but you can convert it into, if there is a base class, you can have that kind of conversion. Otherwise, you can't have conversion. Okay, so you can't store anything in this point except for point itself or something which is derived from point. But then what is stored inside will have information about what kind of object actually it is. So for example, if there is, like, this is point, and then say there is an extension to this class which defines a two-dimensional point, then that two-dimensional point will have another coordinate in addition to x. Okay, but then two-dimensional point can be stored in a point. Okay, so you can have point equal to, and after new you can have a two-dimensional point, and you can store it there. But you can't store any arbitrary object into it. So you can store a point or a derived type only. So there's a limited amount of dynamic typing in C++ or any other language that allows virtual functions or inheritance, and C++, System Verilog, and Java and D, all of these languages, they fall in this category. Okay, now what happens is, if I store, so let's go over it in the next slide. So let me not say it right now. So only a non-static data member need to be, only the non-static data members need to be individualized for each instance of the class. So X was non-static and it needed to be individualized. So that means whenever an object of point class will be created, then there'll be an individual copy of variable X. But point count will not be individual because it's static. So memory will have X as an individual copy. There'll be individual place where X will be stored. This will be common to all the objects of the class. Additionally, you need a pointer to the virtual table to identify vtable associated with the class and the object. With the class the object belongs to. We'll go further, slightly further into that. The pointer to the virtual table reflects the polymorphic nature of the object. So what happens is, if I had a two-dimensional point and I stored it inside point, then the virtual table, okay, will refer to, so two-dimensional point is also going to have a virtual table. The pointer, since I stored a two-dimensional point inside the point variable, this pointer will then start, it will point to the virtual table specific to two-dimensional point. Okay, and then when you make a call, to, for example, print, since the pointer inside here points to another virtual table, now that's the virtual table which reflects the virtual functions of the two-dimensional point. So print will actually call print for two-dimensional point. Okay, so this is how it happens. At compile time, the compiler for a normal function is just going to say that whenever there is a call to a normal function, the compiler is going to say whatever the address to this function is will be called, and the linker is going to make sure that, okay, this is the address, because it's at the time of linking that address will become the linker only will know, because otherwise there are so many functions, and the compiler doesn't know how many functions are there. Only at the time of linking you get to know what all is getting linked in, and therefore addresses are assigned. So at the time of linking, that address will come, but the compiler is just going to put there that this is the symbol, and in this part of the code, call is made to this symbol, and at time of linking, the address will be assigned to that symbol. So a normal function is as simple as that. But a virtual function, the compiler is not going to say that call this address or call this symbol. The compiler is going to say that this is the table. So if you have a call to print, the compiler is going to say this is the table, this is the virtual pointer table, and after two steps, so it will have an offset in the virtual table, in the virtual function table. It will have an offset. So in the virtual function table, after this offset, there will be an address, and you have to call that address. So it's actually calling a function through a pointer. Okay, now, so the compiler is saying whatever is held inside the virtual table pointer, first go there, and over there, since I'm calling print, it's saying after this much offset, there'll be a pointer, and whatever is getting pointed there, call that function. So this print gets called, but in case you are actually storing a two-dimensional pointer, two-dimensional point in that variable, then the virtual pointer will actually point to the two-dimensional, the print corresponding to two-dimensional point, and that will get called. Okay, now there is slightly, like I overstated something over here. This object cannot hold a two-dimensional point, but it's through pointers then. So when you have point, virtual functions will not be visible that way. If you have point, so point is a pointer to a point. Okay, so it's slightly becoming confusing because pointer, I'm using pointer as a concept, and point is a class which is there. So if it's but understand that if pointer were pointer to the class point, and if the type was that, then the actual function is going to get called by whatever that object is storing. So a two-dimensional point will be storing uh, the virtual table pointer for two-dimensional point, and single dimensional object is storing it for the single dimensional. So though we are calling print function on the point, if the point actually is a pointer to a two-dimensional point, then it's that virtual table which gets referenced to, and it will be that function which will be called. Okay, so it all happens through dereferencing. Okay, so now in Verilog, in system Verilog, when you declare point, so though you don't put a pointer over there, by default it is a handle. It's not the value of the class, it's the handle to the class. And the same in D language. So when you have a class point and you declare a variable of that type, actually it's a handle or it's a pointer. In C++, you have to make that pointer explicit, but in D language or in system Verilog language, it's the pointer which will be there inside this PT variable. Okay, so when you say pt.print, depending on whether the actual variable is of type point only or it's of a derived class which could be two-dimensional point, depending on what kind of variable actually it is, the print function is going to go through the virtual table pointer, and it's going to access the virtual table pointer, and it's going to take some offset from there and call the function. In case of single dimensional point, it will be this pointer will point to the table corresponding to single dimensional point. In case of two-dimensional point, it will be the table corresponding to the two-dimensional point. So virtual table, because that will be the pointer a two-dimensional variable will store. So in that sense, there is some to a limited extent, when you are using virtual functions and you are using inheritance, there is a limited concept of dynamism in typing. So the actual object, how it is going to behave, will depend on what type is stored in that object. Okay, so something we'll say here. We already went through it, no? Only so the last point was remaining. The pointer to the virtual table reflects the polymorphic nature of the object. For example, if you are accessing a derived class object as a pointer to the base class, the compiler will have no way to know the real type of the object. Okay, so meaning thereby, if you declare point and then inside point you actually have a two-dimensional point, the compiler doesn't know that it has a two-dimensional point over there, because compiler sees only the type of the variable, not what is stored inside. So the compiler will, for example, if you are accessing a derived class object as a pointer to the base class, the compiler will have no way to know the real type of the object. So at compile time, you don't know whether it's single dimensional point or two-dimensional point. Okay, like we saw in case of factory, at compile time, even after compilation was finished and the executable was created, when you run the test case, only then it is decided what kind of sequence is going to get run. So that's the dynamic nature of the test case. The setting, resetting, and not setting of virtual pointer is handled by the automatically generated code in the constructor, destructor, and assignment operator. So let's not get too much into that detail, but this is how virtual functions get dereferenced at the time of at runtime, and a different function will be called depending on what is stored inside the variable for which the method is getting called. Okay, now given that static data members and functions are shared by class instances, the actual virtual table itself too is shared by the objects of a class. So meaning that by point will have, even if you create 100 points, it will just have one table. Only the pointer will be individualized into each point. Okay, the table itself will be separate. And if you create 100 two-dimensional points, they'll all refer to one virtual pointer table, which will be specific to two-dimensional objects to the class. But the class object itself will have only one pointer to that table. Okay, so this is the extra cost in layout in the memory. Okay, the virtual table keeps a list of pointers to the virtual functions, just as they should be mapped for a given class. In addition to virtual table, in addition, the virtual table keeps a pointer to RTTI. I already explained what RTTI is. Data members of the base class subobject are directly stored in the derived class object. This offers the most compact, so let's not go into too much detail over here. Any change in base class members, adding, removing, or changing members type requires all code using. So these are some more details which are not required right now. When a class definition is passed by compiler, the declaration of the data members and type definitions within the class is read sequentially. So this is also something related to layout. So only if you are deep in programming, then you need to know about this. So I quickly pulled up these slides just to explain what virtual functions are. So let's skip all this portion. So there is some important part here. The non-static data members are mapped in order static data. So we come here directly. In addition to non-static data members, the compiler may synthesize additional internal members like the v table pointer. So this is also not so so specific to what we want to know. Okay, so now we see example of inheritance. So we have a concrete class, concrete one class, and then we inherit from that and make concrete two class, and we make another concrete two alt class. So this one concrete 2 is adding to the functionality of concrete 1, and concrete 2 alt is not having a base class, but it's as if you didn't have inheritance and you added all that information in the same class. So these two merged as concrete 2 alt. This is by way of extension, this is by way of a modification. Okay, so the standard current is integrity of base class objects within the derived class, and this might result in bloating. So let's see what will happen. So concrete one will have the base class object, which is word1, and because the second one is only 1 byte long, so it will become, there'll be some buffer space here, so it will become 8 byte long. In concrete 2, the first object, the base class object will be there, and in addition to that, there'll be another byte, so it becomes 12 byte long. And the concrete 2 alt remains 8 byte long because they can be laid out this way. Okay, but this is not so important. The next part is important. Once you add polymorphism to it, okay, then if you have some virtual functions declared here, then you will have a virtual function table corresponding to the base class. And then if you add another virtual function to the, so it's as if you declare a virtual function here. And one thing you can do is you can override that virtual function in concrete 2. But another thing you can do is you can have another virtual function which is not there in the base class. So in concrete 2, you have another virtual function. So when you do that, so there'll be concrete 2 will have two virtual function tables. One, which is corresponding to the virtual functions defined here, and the other one will have the additional function. So the concrete 2 class, because concrete 1 defines certain virtual functions, so those virtual functions go into one table, and concrete 2, in addition to overloading those functions, it had other virtual functions as well. So it will function tables, and therefore it will have 2 virtual function table pointers. Okay, and that's only like when you map that and you have a complicated case, and you want to know how inheritance is going to work out. So that kind of memory layout you can have in your you can visualize that. Now what happens when you upcast? So upcasting is, so you have one dimensional point, and inside that you are actually storing a 2-dimensional point. Okay, so you had one-dimensional point, the variable itself is one-dimensional point, but the actual, so let me open an editor so that whatever is not written here, I can explain that way. So let me put this way, this, so /temp. So we had, I'm going to put some small D code. So we have a class and we say point, and this has some say int x, and x is small. So this is one data member, and then there is a function, and I'll put the virtual keyword there, though I don't need to. By default it is virtual nt. So I'll say virtual print, so void print. So this function is virtual, and then it says uh, so something like it says write ln x. Okay, so that's how uh, point is getting printed, and then you have class point 2, and then inside that you first you inherit from point 1 point actually, and then you add to whatever was there. So you say int y, and then you say virtual void print, and then you say write ln x and write ln y. Okay, now here in D you'll also have to add a tag called override to this. Okay, so what will happen is, when you in the main, if you say point p, and then you say p equal to new point, and that's it. Then you also have a point p2. Then you could say p2 equal to new point 2, this way. Okay, now at this point we are actually not looking at anything like polymorphism. Polymorphism will happen when I say p equal to, p is of type, no, there is polymorphism here, sorry. So p2 is of type point, okay, and but it is storing it's actually storing a point 2 there. So when we call print function, then because it happens through the function table reference, virtual function table reference, this print is going to get invoked. And that's what polymorphism is about. Okay, now let's look at another thing over here. So I say point 2, which is two-dimensional point, and then I say p2 alt equal to new point 2, and that's what I have declared. Now, there is no polymorphism here because the compiler knows it's point 2. Okay, so though it will still invoke through the virtual table function, but in effect, there's not going to be any polymorphism here. But what we can do later is p equal to p2 alt, for example, which is legal because point is the base class. So the compiler allows us, though p2 alt is of a different type, which is extended type, compiler allows us because it's a derived type. Okay, now p is actually holding a point 2, and when you make this statement, this is actually upcasting. It's upcasting because point is the base class, and it's in a UML diagram. Base class will be on the top and derived class will come uh, below the base class. So the derived classes are in a UML diagram generally placed. So it's not necessary, but generally they are placed below the base class, because normally when you have a hierarchy diagram, something which is more abstract is on the top and the details come on the bottom. Okay, so that's what upcasting is about. You are making a variable which is of a derived type. You are assigning it to the base class object. Okay, so this is all pointers. Nothing but pointer is getting assigned here or there. So when you actually then call print on p, which is the base class, it is going to result in print which is specific to the derived class getting called. Okay, through that virtual function, because even if you are assigning it to the base class, the virtual function table pointer doesn't change, and that's the dynamic information about what is going to be called. Okay, so just give me a second. All right. Yep. And then um, this is upcasting because you are making that pointer refer to the base. So this is the base class, and you are giving a pointer of the derived class to the base class. This will not incur any cost at compile time or at runtime also. Okay, but if you try to do the opposite, and that is p2 alt. Now see, p2 is point in its declaration, but it's actually holding point 2. So you could say p2 alt equal to p2. Now here is something, some illegality in this. The compiler is not going to allow this because the compiler looks at the definition, the declaration of p2, and it finds it's the base class type. And then you are saying assign it to something which is derived type. Okay, now the compiler doesn't know whether this is legal or not. So it will say it is illegal because it doesn't know what is inside P2. So there you will have to say cast to point 2. So once you put this cast, the compiler will put an insert code over here, which will try to convert a variable which is of type of the base class type into the derived type. And in case this variable was actually holding 0.2, this cast will succeed. Otherwise, it will fail. Okay, so this will succeed only if P2 actually holds a 0.2, which is the case here. Which is the case here because we have actually put 0.2 into P2. Now this is downcasting, and this will involve some amount of runtime cost, because what happens is that in this downcasting, the RTTI information of the object of what is actually in the memory will be compared. So what will happen is it will look at RTTI information of 0.2 class, and it will compare it against RTTI information of what actually P2 is holding. And if it is a match, only then this upcasting will happen. This downcasting will happen. Otherwise, it will fail. Okay, otherwise, the result of this cast operation is going to be null. Okay, in system verilog, we will write this as $cast. So you will say $cast P2, and then actually it will be, yeah, it will be P2 alt, no, P2 and then P2 alt. Yeah, P2, yeah, P2 alt and then P2. So you are trying to cast P2 into P2 alt. So in system verilog, it will be like this. So it already knows the type of P2 alt. So it actually, the compiler will then try to, system verilog compiler will then try to cast P2 into P2 alt, and P2 alt is of type 0.2. Okay, so this is how you write it in system verilog. But in D, it is as simple as P2 alt equal to cast 0.2 P2. So now it's trying to, the compiler is saying, okay, if P2 actually holds 0.2, then the casting will succeed. So it will insert that code of comparing the runtime type information. And if it succeeds, then this is going to give you this assignment will happen. Otherwise, a null pointer will come inside P2 alt. So this is what downcasting is. And downcasting should be avoided as far as possible because of that cost of string comparison, because that's a slightly more complicated, slightly more costly operation compared to upcasting. Upcasting doesn't incur any cost. It's allowed just like that. So this assignment will happen no matter what. Okay, this is actually upcasting. So this will happen no matter what. This is downcasting. This will involve runtime cost. Okay, so some people they do downcasting, and after downcasting they call a virtual function. So that is completely not required, because you are doing some you are adding some runtime cost. You could have simply called the virtual functions on the base class. So normally with all these things there, you want to normally call virtual functions on the base class directly, instead of instead of casting to the derived class and then calling those functions. Okay, so that's about it, about upcasting and downcasting and virtual functions, how they are invoked. I didn't go into too many details like multiple inheritance and how interfaces, class interfaces work. So I didn't go into those details because those are a bit more complicated. But this is basically how it works, and this should be sufficient for most of the day-to-day work that day-to-day coding that you people might need to do. So any questions you can ask right now. Otherwise, I'm moving to the next topic, that is the QEMU. And what time is it? So it is already 2:06, and we have 40 minutes left. So I'll be covering QEMU with slightly less detail. That is, I won't install QEMU and run code on QEMU, but I'll emulate that. So basically, the test benching, which involves QEMU, is like inter-process communication between a test bench and another process. So that's what I want to discuss, and I'll be taking some example and I'll be uploading that example on GitHub later. But the code I'll discuss with you and how it works, and I'll run that code and show you how it works, and I'll explain the code. So that I'll do right away, and then later on I'll upload everything on GitHub. So for the timing, I'm stopping to share my screen, and I go for any questions that could be there for polymorphism, for upcasting or downcasting. So please ask if you have any questions. Otherwise, so there are no questions till now. So I can straight away move to EMU. I'll wait for half a minute. If there are any questions, please ask now, because QEMU is or that kind of um, test benching is a completely different topic. Okay, so okay, let's move to QEMU. Okay, somebody is saying something. Can you say that louder?
Sir, yeah, sir, your screen.
Yeah, I'm not
Hello?
sharing right now because I was looking at if there are any questions. So since
Okay,
there are no
yeah.
questions, I'll share my screen again.
Okay, sure, sir, sure, yeah.
Okay, so now we come to QEMU. So I have some code to share. So let's go there. So this one I have deleted, and I maximize my screen, the VNC screen, and then I go to tilde/work and workshop. Okay, so I have some more code here, and that code is where is it? Here, APBQEMU. Okay, so first I'll tell you basically what is it about. So here the slave, we have APB test bench with a slave, which is our DUT. So the test bench is APB master and the DUT is APB slave. And as APB slave, I just have an RTL, which is nothing but a memory. Okay, so I have APB slave, which is slightly parameterized. This has address width and data width. Address width is 8 by default, and data width is 32 by default. So that means there can be only, there's only 8-bit address bus. That means this memory could address 2 raised to power 8, and that would be 256 bytes, okay, or 256 words probably. And the word size is 32. Okay, so then this is the APP protocol. You have PW data and PR data, which are separate, just like Avalon MM bus. APP is very like Avalon MM bus. Then you have enable signal, select signal. The only difference is in Avalon bus, you have separate write and read. In APP, you have write, and then along with that, you have select. So select, when it comes with write, it becomes a write signal. And when select comes and write is not accepted, that is equivalent to read signal in Avalon bus. Yeah, and just like Avalon bus, you have clock and reset and an address bus. Now we implement 256 words because that's what eight addresses can, 8-bit address can manage. So we have 256 words of memory. And this is the APB, a simple implementation of APB. So basically, if it's a write, then it will write into the memory location. If it's a read, then it's going to read from that memory location and return. Now, what we are going to do is we are going to have a very simple test bench, and that test bench is going to be here. This is the top, and the top is instantiating the slave, and then there are BFMs. So we have this BFM right through write app and read app, and we are just like we did for Avalon. So we get a transaction and execute it, and finally have app put, which goes to the monitor, and app done signal, which goes to the driver, goes back to the driver. So a memory mapped bus and a simple one, and this is how it works. And the other day I was trying to explain you auto inst. So this is a good example of auto inst. So there are some local settings that need to be done for Emacs. Okay, so you are saying where to pick up RTL and other things from. So if you are writing code and you are creating a slave, for example, then while writing code, this much was sufficient. So say I don't have this file and I'm creating this file, then while creating, I'll just say, so I'll be here, right? So I'll just say auto inst. Okay, and say I don't have any of these. I don't have this, and I don't have this. So I'll just say this much. Okay, the rest of the code, since it's actually functional part of the code, it's the BFM and other things, so I can manage through templates. But this code is boilerplate because I just need to get the different pins of the slave and I need to connect them at the top. Okay, so if I write this much and just press a couple of keys in Emacs, so the key is going to be Control C followed by Control A. So it's actually going to pick all the signals from the RTL. So it knows that it has to pick it for APB slave. It will pick all those signals and connect here. And then since I set auto reg input and auto wire, so auto reg input, what it is going to do is it's going to look at what are the inputs here in this section. Okay, because it's actually inferring this module from the definition of APB slave. So while it parses the definition of APB slave, it gets to know what are the inputs, and it has tabulated them separately out here. And then I'm saying auto reg input because that's what I want to do in a typical test bench. I want to connect registers to all of them because I want to put some value into these inputs. And for that, the register is the best construct because I can I can assign value to a reg. And then that reg is going to drive that input. Okay, so that's what is going to happen with auto reg input. And then auto wire, so whatever is left, whatever is not into, so for example, had I not gotten into auto reg input, had I not put that keyword, then if I say control CA, so it's still doing that much. Okay, so then if I put auto reg input, so it's going to go here, auto reg input. So all the inputs of various components that would be there, it's going to connect, it's going to create a register corresponding to that. So some issue here, it's auto reg input. or not. Okay, now this boilerplate part is taken care of. So once this taken care of, I just need to create BFMs and I need to put values into these signals in the BFM, in the driver BFM, for example. The clock and reset are treated separately. They are the global signals, and reset also treated separately. So it's not through the BFM that I'll be driving it. But the rest of the signals will be here in the BFM, and we already discussed how this happens in uh, in Avalon. So I won't discuss that again. So it's a very similar code. Okay, now going to what is specific to this test bench. Okay, so what we are doing, the normal is mostly the same test bench, the same way it integrates with Verilog, simulation Icarus Verilog. The difference is here, we have a sequence which actually there's a lot of code here. So which actually is a virtual sequence. So for an APP only test bench, this is a lot of code. So what we are actually doing here is, instead of generating what needs to be written or what needs to be read into the memory, we are getting all that from a different place. And that different place is, so we'll find it here. Yeah, APP socket sequence, and then there are two tests over here. So let me get to those tests first. So in the end, you'll find two tests. So this is one test, Linux FIFO test. Okay, so what's happening here is we are creating a FIFO. We are creating a FIFO on Linux. So let me first explain what FIFOs are about. Okay, so now a bit of the fundamentals. On Linux or on Windows, we can have multiple applications running together, and we already discussed how virtual memory, how physical memory is translated into virtual memory addresses to achieve that. Okay, now in Linux or in Windows, we can have multiple applications running, and these applications in Linux are nothing but they are called processes. So it's a way of parallel programming as well, parallel execution of programs as well. You could have, for example, you could have Firefox running on the same machine as well as Acrobat Reader running on the same machines, and they could be on different processors running simultaneously. The memory, the whole memory which is there is shared by all the threads, but then due to virtual memory, each application will have virtual memory uh, which will access different parts of physical memory, and two different applications will not share memory. So two threads in the same application will share memory, but two threads in which are different processes will not share memory. That's multitasking. So there is multi-threading and there is multitasking. Multi-threading means threads of the same application and they share memory. Okay, but if it is multitasking, then there are two different applications and they don't share memory. Now we want to have a transaction which originates in a different application. We want it to have effect on our simulation. Okay, so let me give you some background why we want to do that. So the background is, for example, you want to so for example, you are creating you are creating an Android application, and not Android application, you are creating an Android phone. And this Android phone, when you are creating, so you will decide some hardware that this is the hardware that we are going to have, and simultaneously there will be a software team which will start working on creating drivers. Now the software team, when it comes to Android, they generally use something called Android Development Kit, which is provided by Google. Now, Android Development Kit is a software which runs on QEMU. So QEMU will create a container, a container application for them. And inside that container application, they'll have Android environment, whether they're working on Windows or Linux, doesn't matter. So inside, just like you have virtual box, you have QEMU, and QEMU creates, in addition to a container kind of environment, it also, you can have a different, instead of, if you are working, say, on an Intel server, you can still have ARM executable running inside a QEMU environment. So your QEMU will be booting Android, and those Android binaries are actually ARM binaries that will be booted there. So the software team is going to work like that. They'll have QEMU. On top of QEMU, they'll have Android running, and there they'll be driving. They'll be creating their drivers and testing it over there. Okay. Now, since some part of the hardware is new, as part of their testing of software drivers, they will want to actually integrate it with a simulation and make sure that their software is able to integrate perfectly with the simulation, which is running in Verilog. So now QEMU is a separate process, and Verilog is a separate process. They don't share memory. They have their own virtual memory tables and virtual memory map. And if QEMU wants to send a transaction to your simulation, then since the memory is not shared, so that's not possible. That doesn't become possible. So what we are going to do is we are going to run a simulation. At that simulation is going to it's going to integrate with another process, and that process could be QEMU, it could be some other process, whatever it is. And it will take instructions from that process of how to proceed the simulation. So let's do that. Okay, so I'm closing this window, and I'm going to tell you something about Linux FIFOs. What happened here? So Control D came out. So I'll go to the temp area, and over here I'll say make FIFO. So this is a command in Linux to make a FIFO. So make FIFO, I call that FIFO as, say, POSIX FIFO, POSIX.FIFO. Okay, so now if I look for POSIX.FIFO, it's a file which has P in the beginning. Normal files will have a dash in the beginning. This is special. So for example, this test.d, which is lying here, if I ls minus la on that, so it has a dash in the beginning. But I created a FIFO which has a P in the beginning. Now P stands for pipe. Okay, so this particular file, though it has an impression on the hard disk as well, but this file will not have any content. Okay, so this is only a pipe to connect different applications. So for example, I can say cat over here, cat POSIX.FIFO. So I want to know the contents of this file. Now this cat will not, because there's no content. But since it's a pipe, it's not an empty file. So the cat command doesn't complete. So it just hangs over there. So let me bring that all that on top so that you can see it more clearly. So cat on this, and it's not doing anything. Then I open another terminal. I already have one. And here also I go into /10. So I see the same file, POSIX.p4. Now, since it's another shell, it doesn't share any memory with the other shell. So I look at POSIX.p4, and this is what it is. And now I put content into it. Echo hello world. And I send it to POSIX.p4. Okay, so when I'm putting content, it put the content and came out. Let's go to the other window and see what happened there. So it printed hello world there. So in a way, I was able to communicate between two shells. So there could be two different terminals as well. So let me do one thing. So let me reduce the size of this terminal somehow. I don't know. This actually VNC is slightly so okay. So we will do it again. So this time we'll put cat POSIX.p4 here, and we'll go to the other window, and we do echo something hello world, hello EUVM, and we put it into POSIX.p4. So here it put it, the other place which was listening to this before gets it. Okay, so this is inter-process communication in Linux or in Unix generally. Okay, so what's happening here is you have two different applications, and they're able to communicate through FIFOs. This is one way. There is another way in Linux. There are actually multiple ways in Linux. So yet another way which is popular is through TCP/IP ports. So this way, where you are doing it through FIFOs, the two processes need to have access to the same hard disk. So these two processes could be on different machines as well, but they need to have access to the same hard disk, which could be through NFS. So this inter-process communication may not be on the same server. These may not be the same machine that these two processes are running on. These could be two different machines as well. But a more popular way of doing it when you're doing it on different machines is by way of something called TCP/IP ports. So you open a TCP/IP port on both the machines, and you open the same TCP/IP port from both the machines, and then from one of them you are sending data, the other one is listening on that port, and you could open two ports, and those two ports, one of them is sending data on one and listening on the other one is doing vice versa. Okay, so this way you have two processes which are trying to communicate with each other, simultaneously trying to listen as well as write into FIFOs or into TCP/IP ports or FIFOs. Okay, so now what we are going to do is I won't be doing QEMU because just setting it up and making it run will take more than an hour. So what I'll do is I'll run a simulation, and this simulation has a request FIFO. So it will take requests from somewhere and has a response FIFO. So it will respond to the process from this FIFO. Okay, when it does that, basically, since it's not shared memory, okay, so we need to have a protocol for communication, because if it's shared memory, then both the applications, both of the threads, actually, applications can't share memory. Both of the threads will have a pointer to the memory, and they'll be able to interpret the contents of the memory. But now, since there are two different applications or processes, then there is no pointer concept. You have to send the content itself. Shared memory means memory is common, and you just send the pointer to the transaction that you are wanting. You want to transfer from one thread to another. Okay, but here it's not a transaction pointer. The transaction itself, the content of the transaction itself has to be sent. So what we do is we go for a protocol, and that protocol I'll describe some. I've described already done that. So this is where. So we are here. We are sending it to the socket. Response to the socket. So we take a payload, and this payload will be sent to the socket. Okay, so we have header and payload. These two things will go to the socket. So you see this happens via some kind of byte packing. So you take the transaction and you pack the transaction into a memory buffer, and this sequence of bytes you send over the socket to the other process, and over the other end, you interpret back that sequence of bytes and create a transaction out of it. Okay, now this could be useful, for example, if you are interacting with an emulation platform, and that emulation platform is running on another machine, and your verification environment is running on a different machine. So how do you communicate between the two? You communicate via inter-process communication, and then you have to send the content. You can't just transfer a transaction through its handle. So you have to create a byte buffer and send it. Okay, so this is how you do it. So we'll run this code, and then I'll tell you how it all works. Read data, get request from socket. So this is where I'm getting a request from socket. So there is a structure which will be more clear from another file actually. So when I run the simulation, then I'll be running this Ruby file. Okay, this is where I'll send the transaction from, and the transaction will be like this. So if it's a write transaction, then it will first contain information about endianness, because these could be two different machines. Even QEMU is a different machine in that sense, because QEMU could be running big endian ARM edition, for example, instead of little endian. Little endian and little endian are okay because they have the same byte sequence and the sequence of bits within the byte, or actually sequence of bytes within a word. Okay, but little endian and big endian communication is slightly more tricky. So first we send endian information that this is the originator of the request is of this type, of this endianness, and then we send packet length. This is the data, this is the total data I am sending. Then there is a version information and ID information. Each transaction has some ID, and version is about the version of communication, the protocol that we are using. So it could be 1.0 version, and later on if we revise it, then 1.1 information, and so on. Then there is an op information which says whether it's a read request or write request. So because we are dealing with APB, so this is the APB control signal, read or write. Then there is data length. How many? So we have packet length in the beginning and data length later. So packet length in the beginning because up to this, up to this is the meta information. It's the information about the packet itself, and later on is the transaction information. Okay, so the transaction constitutes of read or write, what kind of operation it is. Then we are sending data length, how many bytes or how many words to write, and starting at what address. Okay, so all this gets packed up over here. So C means one character. This will be 8-bit. This is long. So this is packet length, which will be 4 bytes of data. Then this is short, which will mean this is 16-bit of data. And then again a long, which means ID, which is okay, 1, 2, 3, 4. So ID is again 4 bytes of data. And then we have character, which will be ID, which will be operation. So operation is either read or write. So we can manage that in one word, 1 byte. So then there are two integers, which are 0 and data length. And finally, no, actually, let's see it this way. Address uh, is in terms of 32-bit. Q means so you can check up the manual for this pack instruction, and you'll find it there. Like what Q, probably Q is 4 bytes and L is 8 bytes or something. I don't remember fully. Okay, so that's how this gets communicated. We can also trace because the same interpretation will happen on the embedded UVM side. So this data will be sent from Ruby, and it could have been from QEMU, from some C or D executable in QEMU. The important thing is it's happening inter-process, so it's happening via queues, via FIFOs. Okay, so we send this data from one end, and this was the write request, and so we send it to the socket. Okay, this is the same FIFO. So the same FIFO we are initializing it as a write FIFO. So we send it from here, and then we flush it because we want all the information to go in. And we the same way we have read sequence where we make a read request and we flush it. And then there are some control sequences which are for example, the application which is controlling the simulation. It's sending a request for terminating the simulation. So that kind of requests are also there. So then this is the pattern which is in Ruby, and the test bench is going to interpret this information and run the simulation accordingly. Okay, in the end, we'll have the test bench terminating the simulation. So let me uncomment it, and as you can see, there are sleep in between, 2 seconds of sleep, so that we can follow up how the whole sequence is going. Okay, so let's see. So we are here. I'll put my path. Okay, so I have to take it from a slightly different place because of FIFO specific things. So I'll check those things in later. So I pick it from code, embedded UVM, and LDC build, LDC 2.1.21, and bin. So this is my path. So when I say type LDC2, just to confirm this is my path. Okay. Now I go to the workshop area. I go to the workshop area, and there I go to the APPQEMU, and inside that there is a sim directory, and I go here and I say make. So okay, so make, because make is compiling the BFM part, so that part is clean. So we'll say make clean, and we'll say make again. So my test bench is getting compiled. Okay, here I'm using LDMD2 instead of LDC2, but it's just a different flavor to execute the same compiler. So just the command, the particular command flags will be slightly different. Actually, they are not even different here. So everything, instead of fpic, it will be that in case you use LDC2, it will be that PIC model slightly more detailed. Okay. So that's how this got compiled, and now I'll run simulation. So if I open the make file, then the default simulation is, I think, through TCP/IP. I'll change that to FIFO. So okay, sorry. So run command is for FIFO only. So this is the FIFO test, Linux FIFO test. Okay, so I'll just say make run. So now the test case is running. Actually, this test case is putting too much information out there, but that's okay. So it's running, and probably it's giving information in debug mode. Okay, so it's running, but it's in debug mode. And then from the other window, because I want to emulate the other process, from the other window, what I'm going to do is I'm going to run the Ruby command. Sure. And there app UEMU, and there I say I go to the same directory because that's where my FIFOs are, and I run the Ruby command, Ruby, and then that command, which is the Ruby command, socket mm. Okay, let me see, Avalon mm. So I say Ruby Avalon mm dot Ruby. Okay, so there was 2-second delay between the commands. So it's slowly sending read and write requests. And over there on the simulation front, we see those commands getting executed. And then in between, there are 256 commands which don't have 2 seconds delay. So those 256 commands will get executed. And then again, the last few commands have a 2-second delay. So those are getting executed. So the Ruby process over here is controlling the simulation. So this could be a QEMU process or any other process. It could be from another machine. But this is how you interface a simulation with a process which is separate from simulation. Okay, so this simulation completed because in the end there was a term request. All right, so we can run it. Okay, we probably want to look at the Ruby file once more. There's very little time left. So this is what we executed. We had these functions defined on the top, and Ruby is just like Python. Some of you may not have heard about it, but it's very popular for web design, and it's a scripting language like Python. Okay, so I create a class and then the class object, and then I create read and write methods on it. I call those methods, and in the end, I'm telling the simulation to end. So this is like a slave simulation, which is getting controlled from elsewhere. This same thing, if you control it from QEMU, and your reads and writes into the device actually come to the simulation, and the simulation responds to those. So it becomes useful for hardware software co-verification. And it could be taken to, for example, to the to verification, which is co-simulating, which is a test bench co-simulating with an emulation platform, for example, which is on another machine. Okay, so I'll be uploading all this code on GitHub, and then I'll share all the information with you on the forum. So by tomorrow I'll do that because I don't have to prepare for anything today. So I have time to put this to create these documents, these little tutorials, and I'll be putting it on the web. Okay, so that completes the last part, the last session that I had. Tomorrow we have a session with Intel. I'll be there. And today we have a quiz at 3 o'clock. So we have the quiz at 3 o'clock right now. I'm ending this session. So over to Firoza ji.
Yeah. Good afternoon, sir. Thank you, sir. Dear participant, thank you for joining us for today. So I request you to disconnect right now. We will be having the quiz at 3 o'clock. I will request you all to please be in front of the system before 3 o'clock and submit the quiz before 3:30, because again there will be some issue and related to the complaints that we are receiving regarding the internet problem, that we cannot help. You all can also understand. That is the only reason why we are giving 10 minutes of grace time to all the participants. So all the best, dear participant. Please connect for the quiz at 3 o'clock. Thank you, Puneet sir.
Okay, see you all tomorrow.
Yes, sir.
Okay.
Thank you, sir.